All right, we are doing diffraction gratings today, and if you are going to follow along in your notes, we're at the bottom of page 10. In class, we did the first activity, and that's on page 10. Today, on the video lesson, we're going to do page 10, page 11, and then page 12. So we're going to go ahead and see if we can finish all of those out. Before we do that, let's just do a quick little note on our schedule for next week and then the week of Thanksgiving. So Tuesday when we get back, we're going to start a lab, and that'll be the laser lab. Reminder, the sound lab is due on Monday, so at the beginning of the hour, so we need to get that done. So if you need to come in on Monday, send me a text, and we can work that out. I'll also be in here very early Tuesday morning as well. All right, Wednesday we'll do the laser lab. It'll probably take 2 days. One day to probably collect data, and the other day to probably process it. And then worksheet 14.1 will be due on Wednesday, and then after today's video lesson, you'll have enough information to do worksheet 14.2. And so I'll give that to you today through the video. I'll actually attach it to the email that I send you. But if you want a hard copy for yourself, without printing one yourself, then you can pick it up Tuesday and then do it for Wednesday. It's up to you guys. Friday, we're doing Q&A, and then Monday is the test, and then we'll go over the test on Tuesday, and then obviously Thanksgiving starts on Wednesday. So there it is. So let's go through diffraction gratings. You had your hands on diffraction gratings. We're at the bottom of page 10 right now. You had your hands on a bunch of diffraction gratings on Friday. And lasers, and you work through some relationships. What happens when the distance between the laser and the diffraction grating changes? What happens to the interference pattern? What happens to the interference pattern when the distance between the diffraction grating and the screen increases and decreases? So, and then wait, let's see, I think you had one more, like color as well. So you had some relationships there that you worked with, and I think we all discovered those together. I think it went real well. I'd like to go ahead and give you the equations for diffraction gratings, and what's nice is they're real similar to some of the equations we've been dealing with double slit and single slit interference patterns. And then we'll go ahead and work you through some examples. So if you go to your equation sheet, this doesn't even make sense for me to even try to write these out because they're already on your equation sheet. Here's your equation sheet, and you can see that the equations look pretty darn similar. So you have m lambda equals d sine theta. M is the orders, and you go from 0, 1, 2, and 3. D is a little bit different. D is going to be the distance between the grading lines. And we did that on Friday at the very top of, I think, page 10. We did an example of that. I think it was the third bullet point on page 10. And you can kind of work through that and check that out and see how that goes. But it is there for you. Let's see, M deals with the maxima. So we're looking for bright lights. Remember, double slit was with maxima, bright lights, but single slit was with minima. And then xm equals m lambda over d. M is 0, 1, 2, and 3, and this is going to be a distance from the central max to the mth line. So double slit and diffraction grating equations are very, very similar, just one slight distance, and that is how they define D. And I think that's it. That's all I'm going to give you. So we're going to use these two equations, this guy here and this guy, to go ahead and go back through activity number 1 and just verify everything that we did in the lab. We're going to verify it with the equations and see if that makes some sense. So let's go ahead and get started. We're on activity number 1. We're on page 10 of your notes. And I'm just going to kind of roll through these. I'm not going to spend a lot of time on them, but you do need to kind of be aware of them. So, first question, what happens to the diffraction pattern if the distance between the diffraction grating and the screen is held constant and the distance between the laser and the diffraction grating changes? So what does that mean? So if I have my diffraction grating, so I'll kind of show looking like that, and this is going to be my screen, and then this is my laser. So the light comes through, and then we get all our maxima. So the question is what happens to this pattern, the interference pattern, if the distance between the laser and the diffraction grating changes. That would be this distance. Well, if you go to your equations, we've got two of them. The first one is m lambda equals d sine theta, and the other one is going to be xm equals m lambda L over d. So if you just check this out, this distance here is not in any of these equations. This L is the distance between the diffraction grating and the screen. D is the distance between the slits. So there's no change. And I think that's what you noticed when you did it on Friday, that whether or not this laser is far out or close in has no effect on the diffraction grating or the interference patterns that's produced. All right, let's go to the next one. Grab me something to drink. All right, what's next? The next one says, what happens to the diffraction grating pattern, or the diffraction pattern, as the distance between the laser and the diffraction grating is held constant, and the distance between the grating and the screen changes? All right, I'm not going to double my or redo this diagram because it's already right here. But this time we're going to change L, and L is in this equation right here. So we're going to just go ahead and rewrite it. So xm equals m lambda L over d. All right, so if the distance between the grating and the screen, which is L, goes up, then x goes up. So x then would be, so this would be, if I go back up to here, this would be m equals 0. Then the x in this equation here is the distance between m equals 0, m equals 1, m equals 2. It's that distance. So if the distance between the grating and the screen increases, then the distance from here, m equals 0 to m equals 1, is going to go up. And I think I can illustrate that, or at least demonstrate that. You actually did it on Friday when you had the diffraction gratings in your hands. But so I'll see if I can see if this actually works here. So I'm going to go ahead and send a laser light through here, and you can see the diffraction pattern. And if I increase the distance between the screen, so now it's close and now it's far, notice that the diffraction pattern increases. The distance between the maxima, which is the brightest one in the middle, and the others goes up as L goes up. That would be distance from the screen, which is the piece of paper in this case, and the diffraction grating. So now it's close, and now it's far, and that diffraction grating spreads out. Okay, the next one, letter C. It says, now collaborate with another group that has a different colored laser, and describe how a different color affects the diffraction pattern on the screen. So let's see if we can run through that one. We can use actually either equations to describe this one. So they'll use this guy here. Kind of dial this in a little bit so you can see it. So we'll go xm equals m lambda L over d. And so if we make the wavelengths shorter, that would mean like going from red to green to blue, then the distance between each maxima is going to go down. Let's see if we'll demonstrate that here in just a bit. Here's the next one. So we got m lambda equals d sine theta. And if I decrease the wavelength, that would mean like more blue, then the angle between the maxima, or how far out the pattern is spread, will go down as well. So I'll go ahead and get two lasers out here. I've got a red one and a green one. I'm going to kind of pull this back out. You did this in the lab on Friday. So here's this guy, and you can see how far they're spread. Now, if I go to a shorter wavelength, they should, according to this guy right here, it shouldn't be spread out as much. They should come together a little bit more. So there's that one. And if I hold everything else constant except for the color, you can see they get closer together. That should be a blue. I'm not sure if that's coming out on a video real well. So here's red. You can see if they're spread out a little bit more. And then there's blue. And that illustrates it. Okay, the last question, letter D, just verifying the equations. Obtain the black diffraction grating that contains individual gratings, and here it is here, of 100 lines, 300 lines, and 600 lines. How does the number of lines affect the diffraction grating pattern? All right, so we're going to go ahead and use this equation. That will be m lambda equals d sine theta. And let's think this through real quick. If as you go from 100 to 300 to 600 lines per millimeter, D is not 600 lines per millimeter. D is actually the reciprocal of that. So as you go from 100 to 300 to 600, D actually goes down. So if I say the distance between the lines goes down, what's going to happen to the diffraction grating? Well, M is going to stay the same. The wavelength will stay the same. That means it has to get more spread out. So if I go from 100 to 300 to 600, D goes down, the distance between the lines goes down, and it should be spread out. And we'll try to illustrate that right here on the screen. So I'll take my red laser and hold it out here. And so there's this guy. There's the 300. You can see it spread out. And then there's the 600, so it spreads out even more. So there's close in, spreading out, and spreading out even further. All right, that's page 10. Let's flip over and go to page 11. All right, page 11 deals with example number 5. And I'll just go ahead and read this first, and then we can kind of see if we can answer the questions as we go along. So the first question, or the first introductory part says, a particular diffraction grating produces an m equals 2 spectral order at an angle of 30 degrees for light with a wavelength of 500 nanometers. How many lines per centimeter does the grating have? Okay, so let's draw, I guess, a picture first, and then we'll see if we can make some sense of it as we draw it. So let's put the screen, kind of dial this in just a little bit. So I'll make this the screen. I'll put my grating over here. So there's my grating and the lines. We'll have the laser light come in, and then if it goes straight through, that's m equals 0. There's m equals 1, and then m equals 2. All right, now let's see. It says how many lines per centimeter does the grating have? All right, that's a pretty straightforward one. So we're looking for D, since they asked for lines per centimeter. Let me put some numbers on my diagram here as well. So we've got 500 nanometers, and for the second order, so this is m equal. I already got those labeled. So for this angle, for m equals 2, it's going to be 30 degrees. All right, and so we're looking for lines per millimeter. All right, so that's going to be D at first shot. So we're going to say m lambda equals D sine theta. D then is equal to m lambda over sine theta, and just a matter of plugging stuff in. We want the second order. They gave us the wavelength of 500 nanometers, all divided by an angle of 30 degrees. So this will give us D, and if we punch all that in, we're going to get 2,000 nanometers per line. Now, I don't want nanometers per line. I don't want meters or nanometers per line. I want lines per centimeter, and that's what they have up here. So I'm going to go ahead and kind of tweak that a little bit and see if I can make this work. So to do that, I want to flip this upside down. I want to take the reciprocal of it. So one line for every 2,000 nanometers, or one line is every 2,000 nanometers. All right, and we want to convert that to, let's see, lines per centimeter, because that's what they asked for up here. So lines per centimeter. So the first thing I'm going to do is, I'm just going to do a quick conversion. I know that nano is the same thing as times 10 to the negative ninth. So I'm going to erase this guy. I know I drive you crazy. That's my goal in life. And put in 2,000 times 10 to the negative ninth meters. This is how it makes sense for me. And then I know that 1 meter equals 1,000 centimeters. So when I plug this into my calculator, come up right here, I can take 1 divide by 2,000 times 10 to the negative ninth, and then divide by 100. And that gives me then 5,000. So this particular grating that they would be dealing with in this problem has 5,000 lines per centimeter. And there it is. Okay, the next question. At what angle can the m equal 3 order spectral order be seen? All right, we're looking for angles. So the equation that's going to give us angles is m lambda equals d sine theta. We want angle, so we'll solve for theta. So theta is going to be inverse sine of m lambda over d. So we have sine inverse m, we're doing a third order, times the wavelength, which was 500 nanometers from above, divided by d, which I just calculated, which is 2,000 nanometers per line. And now it's just a matter of plugging this stuff in. On this one, if you notice, the nanometers, I have a nanometer on top and a nanometer on, so that's actually cancel out. So really it's just 3 times 500 divided by 2,000. And then I got to do inverse sines. So let's see if I can squeeze this in. So here it is. So I'll go 3 times 500 divided by 2,000, and then inverse sine of that answer. And I get about 48.6 degrees. And there it is. All right, part C. Part C says if white light, and really I should cap that next year so we can stress that. So if white light of wavelengths ranging from 400 nanometers to 700 nanometers were used, what would be the angular width of the spectrum for the second order? Okay, let's just think that through real quick. I'm going to go back up to my diagram up above and look at this. Now, in this case, in letter A, we had just one color going through, and that was 500 nanometers. This time, we're going to have a whole spectrum of colors. We're going to have white light passing through. And so when white light comes through, what you'll get is, you'll get a spectrum, Roy G. Biv, for the first order. You'll get a spectrum, Roy G. Biv, for the third order, or second order, and you'll get a spectrum for the third order. So you have like little bitty spectrums, little spectrum here, spectrum here, spectrum here, or another way of thinking about it, rainbow here, rainbow here, rainbow here. We want to know, for the second order, what will be this angular separation. So let's just kind of think it through real quick. If I go back to my equations, and I look at the equation for this, which is going to guide my thinking, it's going to be m lambda equals d sine theta. Let's just think about red light. Red light has the longest wavelengths, which means it's going to have the greatest angle. So when this passes through, for m equals 2, the red will be on top and the blue will be on the bottom. So it'll be Roy G. Biv coming down. We want to know, what is this angle to the blue, and then what is this angle to the red? And we want that difference. We want to see how we really ultimately want that angle in here. So I'm going to have to do this equation twice, solve for theta for the blue, and then solve for theta for the red, and then subtract them. All right, so I'm going to go down here. I'll do red first, or I should say the longest wavelengths, which will be 700. In this case, they give me 700 right here. And so I'll go ahead and run through those. So I'm going to go ahead and solve for theta. So theta is equal to inverse sine of m lambda over d. Theta is equal to sine inverse m. We want second order times the wavelength, which is 700 nanometers, all divided by d, which we had above, which was 2,000 nanometers per line. All right, again, my nanometers cancel out, and if I plug this into the calculator, I should get 44. You can verify this if you like. 44.4 degrees. All right, I'm going to do the same thing now for the shorter wavelengths, the bluer side of the spectrum. So m lambda equals d sine theta. Theta equals inverse sine of m lambda over d. So theta is equal to sine inverse 2 times, this case, 400 nanometers all over 200 nanometers per line. And if you do the math on that, it comes out to be 23.6 degrees. So if I go back up to my diagram, this smaller angle here is going to be 23.6. This is like for the blue side of it. And this longer one is going to be for the red, and that'll be 44.4 degrees. And we want this guy right here. And so we're just going to basically subtract those. And when we subtract them, we get 20.8 degrees. And that's how far that rainbow is spread out when it passes through those diffraction gratings. All right, moving on to letter D. Letter D says, what would be the angular width of the spectrum? So same question they had up above for the zero order. Not for the first or second or third. We did second last time. But for zero. Well, let's go back up to the diagram. What's that mean? So white light's going to pass through the grating. This is the zero order right here. And what it's asking for is, what's that rainbow going to look like? How spread out will that rainbow of colors look like, Roy G. Biff? Well, the answer on this is a little deceptive, but I think if you let the equation guide your thinking, you'll pick up on this quickly. So I'm going to go ahead and go back to the equation we were working with, m lambda equals d sine theta. And if I look at this one, if I'm dealing with the zero order, then this has to be 0. That means this whole side becomes 0. Well, the only way to make this side 0, because d won't be 0, is to make sine theta equal 0. And to make sine theta equal 0, theta itself has to be 0, because sine of theta, if I come over here, sine of 0 is 0. So what does that mean? It means that regardless of what wavelength I pass through here, it's not going to have any separation. 400 nanometers and 700 nanometers are going to be the same separation. So actually, there will be no rainbow here. Right here will be all the colors put together, and all the colors put together will become white light. Right there. So the answer on this one, what would be the angular width? The angular width, theta, would be 0, and that would imply that you would have white light. Okay, the next question. What happens to the angular width of the spectrum as the order increases? Same equation. M lambda equals d sine theta. As the order goes up, that separation will go up as well. And so that'll be increase. And then the last question, and I'm going to have to kind of fill in the gaps on this one a little bit because I need some images. Letter F says, how would your previous answer be useful to astronomers? Well, here's how it's useful. There's a star that might be way out there. That star's light gets all the way to the Earth, and what we do is we take that light from the star and we pass it through a diffraction grating. That diffraction grating takes the colors of the rainbow, red, sorry, red would be on top, all the way through blue, and it spreads them out. And when we spread them out, we can see the spectra of the stars. And we talked about this last chapter. If we can spread that light out, then we can see all the individual lines inside the spectra of a star, or spectrum of a star, and then we can figure out what elements are in that star based upon the spectra. So basically, we use a diffraction grating to split the white light. So instead of using a prism, we use a spectra or a diffraction grating to split that light, and then we use that light to figure out what elements are inside that star. And that's pretty cool. So when we come back on probably Thursdays when we'll go through it, because we'll do the lab on Tuesday and Wednesday, we'll go through and I'll show you how that works with astronomy. All right, that's page 11. Let's go to page 12, last page. That leads us right into a discussion at the top of this page of spectroscopy. And spectroscopy is exactly what we just talked about. It's the science of studying the spectrum of different types of atoms and molecules. So a branch of physics that deals with the study of atoms and molecules as observed via diffraction gratings and spectra. And on Thursday, I'll see if I can show you some examples of what that actually looks like. All right, the next question says, can wavelengths of light from different orders be the same distance from m equals 0? Another way of asking that question. Can angles for different orders be the same for two different wavelengths? Okay, let's start this out with a diagram. So here's the screen, and here's the diffraction grating. And what I'm going to do is I'm going to go ahead and I'll use different colors here. Maybe this will make more sense. I'll send red light through, and if I send red light through, red light's going to hit up here. And maybe this will be red light for, I don't know, red light for order number 1. All right, now let's say I got a blue pen. Let's say I want that red light, or now I'm going to shine, instead of saying red light, I'm going to shine blue light through. Well, if I want to have that blue light hit at the same spot, same distance from red, or from m equals 0, if I want the blue light to make that same path, it's not naturally going to do that from the same order. Blue light, we just did this, is going to fall a little bit below that red light. We did that in a previous question. So how can we get that blue light to fall right on there? Well, it would have to be blue light from a different order. So if we use the equation to guide our thinking, m lambda equals d sine theta, d is the number of, let's see, the distance between each line. That'll be constant. We want theta to be constant as well, because this is going to be m equals 0 here. And we want, all right, we want that angle in here to be the same. So if the wavelengths become more blue, that means the wavelengths are going to go down. Then I have to use a higher order to get the red light and blue light to fall on the same place on the screen. All right, that was a lot. If you need to review that, listen to it, dissect it, go ahead and do it. Letter H. Moving on. Letter H, here's the question. There is a limited amount of orders that can be obtained from a given diffraction grating. Derive an equation that governs the highest order that can be produced by a given grating. Okay, let's start with the diagram. So we'll do a screen here. We'll do our diffraction grating. And then we're going to send light through that diffraction grating. We know that this is right here going to be m equals 0. This will be m equals 1, m equals 2. The question is how many orders can I go? And there's actually a limit to it. And here's the idea. If I keep going out, there's might be m equals 3, I keep going 4, 5, 6. Eventually, these lines will never get, these lines as they extend out will never get to the screen if the angle here becomes 90 degrees. If this angle becomes 90 degrees, these lines will never ever get to the screen. Anything less than 90 theoretically will get to the screen. So if I start with m lambda equals d sine theta, there is a limit to it, and that's when sine theta, that's when theta equals 90. So let me plug that in. This will be d sine of 90. Well, what is d sine 90? Or what is sine of 90? So if we go back up here, I know some of you guys know this, sine of 90 becomes 1. So that means this whole part becomes 1. So m lambda equals d, and that's going to be for the maximum. That's when, let's say, how do I want to phrase that? That's when m is at its greatest. So if I solve, m then is going to be d over lambda. So there's the derivation. Simple equation. M equals d sine theta. This will be the biggest order that can possibly be captured on the screen. Anything more than that won't be captured on the screen. All right, and then the last one. Based upon your previous equation, that doesn't make sense. Obtain the highest number of orders. I'm sorry, based upon your, let's see if I can read that. Based upon your previous equation, to obtain the highest number of orders, you should want a grading that has a high number of lines per minute or a low number of lines per minute. So that is actually okay. So let's use the equation to guide our thinking. We just derived it. So this is m is equal to d over lambda. If we want the highest number of orders, so as many orders as possible, then we want this wavelength to be short. We want it to be small. So it would be, oh no, they're not asking about wavelengths. They're asking for lines per millimeter. So then d will have to go up. But, now listen to this. This is the distance between the lines. The distance, as the distance between the lines goes up, the number of lines per millimeter actually goes down. So we want to have as few lines per millimeter, and if we go as few lines per millimeter, then we'll have as many orders as possible. And if we pull this guy back in, remember 100, 300, 600, this side over here would be few, some, and then many. And if I put these in here, you can see that there's some, there's more, and then when you have 100 lines per millimeter, you get the most orders that can be produced in this particular arrangement of 100, 300, and 600. All right, I'm going to start you out with letter J on Thursday, so we'll include that because I got to do some images. So that's the scoop on the video. It's 33 minutes long, 34 minutes long. I'll attach worksheet 14.2 to this email. If you wanted to start on it over the weekend, that's fine. Or if you want a copy from me, I'll have one ready for you when you get to school. Otherwise, have a great weekend, and we'll see you on Tuesday ready to do a lab on lasers.